Episode of Applying Math Where It Doesn't Belong. We have tic-tac-toe, and if you've ever wondered to yourself, how many possible games are there in tic-tac-toe? There are 6,046 unique orderings of X's and O's to a complete game in tic-tac-toe. So, now you know. This is what we did in study group this week. It's actually been 2 weeks that I've been working on this. This is the specification for tic-tac-toe without a winner. So it doesn't understand when someone won. It just plays the game until quote unquote deadlock, until the game just has no more plays. So, the basic configuration is you have a board here with a 3x3. You can play X's and O's. Dash is just nothing, it's just empty. And then there's set operations to determine when there are open cells to play. Then each turn, if it's the current player's turn, then X gets to go and then you switch players. Or it's O's player's turn, then O goes, and then you switch players. So this is the state machine. The next state is always switching between X's and O's until deadlock, when no more player can go. And X's and O's is there exists a row and a column in the open cells where you can put an X in the O in that row and column. So in full math syntax, there exists in open cells, and the next state of the board is this state of the board with that row and that column changed to an X. So this is just putting an X at that row and column in the next state. So that's how it works. You can run this with the checker, and it will run through all orderings of tic-tac-toe, and then it displays one of them that has a deadlock. So we'll need to define a win condition and then actually define strategies like looking for corners and looking for middle. But this is a complete game of, you can see the X's and the O's are filling in as the math is playing that game. So that's another week in applying math where it doesn't belong. Thank you.